Okay. Hello, guys. You see me okay? You see me okay?
Yeah.
Okay. Okay. Today is times and space number 2, or space and times, whatever. Okay. What about the previous one? How was it? Did you answer the questions?
Can you give me a piece of paper? Where is it? No, Peter, you had it. Okay, so there was 3 questions. We didn't get the third one because we didn't understand it, but the first 2 we did. So the first one was calculating your frequency.
Okay.
And it turned out that we're all vibrating very, very quickly.
How fast?
Like it was, if I recall, what was it?
21 to the power of 50.
No, 10 to the power of 50 or something.
So 10 with the 50 something zeros, right?
Yeah. And
So you can imagine how fast you're oscillating, right? Vibrating.
Yeah.
And this is true, actually. This is real physics. Okay. So just nice to know. Oh, the second one?
Special attention to the units, and the units were correct. And the second one was to calculate the black hole radius. And that black hole for us was, the
Smaller than a hydrogen atom.
Oh yeah, it was 10 to the negative 15 meters.
No, it was 10 to the negative
25.
26.
25 or 26, yeah.
Mm-hmm.
And the hydrogen atom is 10 to the negative 10 meters.
Okay, good. So now you understand that you are very small and oscillating very fast, right? All this is just an illusion.
The slower you are, the slower you isolate.
No, you're just to understand that your body is just illusion. You know, you are very small and vibrating very fast. Okay, what's the third? Why you don't understand? What was the third question?
We didn't really understand the question itself. Where's the piece of paper? I don't have it. What was the third question?
I don't remember. The
Yes, I
third.
figured out what it was asking, but I couldn't.
I don't really. Okay. Just questions. No, I don't have it. The third one. Okay. What's your radius? What's your frequency? How many? Jesus, I cannot read how many something is in you?
How dense are you?
How many seconds?
What do you mean how many seconds are in this?
Yeah, I didn't get that question.
Okay, remember this natural measuring unit system, where all the constants are equal to 1.
Yes.
So I still ask you to think about it. Okay, you take this natural system, you find out what is your weight in seconds, how you weigh in seconds, calculate it. Okay, you got it? In seconds, because the units are the same, so they're all seconds or light seconds.
I seriously don't get it. I don't even know where to start.
Okay, so you think about it. Okay, just I'll tell it again. Okay, you have all these constants, right? I wrote it for you, like Planck constant, right? The speed of light constant and gravitational constant, right?
Yeah.
You have them, right?
Yeah.
So if you have them, you can come to a natural system of measuring units, where from the beginning, meter, there's no meters, there's only seconds, right? There is second as a main unit, second, right? For example, so I suggest second is a main unit, right? Then the measure of the distance is a light second. So how big distance light can come, for one, okay, for 1 second.
I think I get it. Okay.
You can calculate it, right? Now then, after that, okay, right? You can calculate how much energy is in seconds, because you have oscillation and h is a Planck constant, right? Oscillations in second minus 1, right? So you can use it, put h1, and you can say how much energy and mass, right? is in seconds, and then calculate seconds. Okay, so think of it and make it, okay? We'll talk about later. Okay. Now we'll start from our thing, right? So today we'll talk a little on the laws, the main principles of physics, and main principles not of like physics as per se, but the physics that was like in the previous centuries, because the last century, 20th century, is a big century, a big change in physical laws. So, and we'll talk on them later. But today we'll talk on physics that get this shape of physics like the recent few hundreds of years, right? So it started from the biggest thinker of all times, sometimes considered the largest, the smartest thinker of all times. It's Aristotle. It's a Greek philosopher and so-called natural philosopher, whatever. He lived in. You have some question, Antosha?
Huh?
You said asking
No,
something?
Vita is asking, was Aristotle really the smartest?
It's considered by many. You know, there are how many people, so many thinking, right? So people can talk different things, but Aristotle is considered one of this. Like for example, I'll give it to you. Like what he was an originator, so he was the first who really originated. He created. So it's not just he worked on it, right? But he created the whole branches of science, and not only science, like just a few of them. He was creator of physics, originator. Before Aristotle, there was no such field. There were people talking about some things, but there was no such field. Biology, logic, the mathematical logic that we use now, it is Aristotelian logic, which just transformed written in mathematical symbols, but it's still his logic. Ethics, it's the science of morality, right? Aesthetics is the science of our taste and everything, right? Poetry is a science, right? Psychology, linguistics, economics, politics, government policies, and many more.
That's all Aristotle?
That's all Aristotle. So you may think whatever you think of Aristotle, but that kind of man, was it, right? Now Aristotle as a philosopher, he was apprentice of another great philosopher, Plato. You know Plato, right? Who was, in his own order, he was apprentice of Socrates. Socrates never written anything. He considered that writing is bad for philosophy, so he only talked to his apprentices, to people who followed his philosophy, and Plato was considered as a father of all Western philosophy. The main guy. His apprentice was Plato, Socrates, right, was considered, right? Plato was his apprentice, and Aristotle was apprentice of Plato. So there's just strange line. Also, at the same time, Plato was a teacher of another great world figure, Alexander the Great. You know, the great conqueror.
Really?
Yes, really. He was a teacher. Yes, he was teacher. Aristotle was teacher of Aristotle the Great, and Alexander the Great. Alexander the Great was a very smart man, by the way, too. He was not only conqueror, but he is a pretty smart philosopher and everything like this. He was apprentice of Aristotle. Yes. Also, another two big kings of that time were two apprentices of Aristotle, and their names are, I think, Ptolemy and Cassander. So Alexander the Great and two of those. So, but anyway, we're interested in his physics, right? In his physics. I wouldn't talk a lot about physics of Aristotle, but the main interesting thing is that what he noticed, that something can move only when the force is applied.
Inertia.
So force is applied, something is moving. You remove the force, it stays.
not the same as inertia.
Isn't this Newton's
And this, yes, this is Aristotle's physics. And there are a lot of other things that he found out that he was describing this and this. You should understand, it's not like modern mathematical physics, right? He was what was called natural philosophy, but he found a lot of features in there.
Can you please give us an example of an object which is not moving unless you apply force to it, and stops moving when you stop applying force?
Okay, I would give you another thing.
This is a car.
Car, okay, car. What car?
Like when you put pressure on its wheels, it moves, but when you don't, it doesn't move.
No, light can be stopped, right? I don't know, probably like you know light from the sun. You put your hand and light is stopped. So you force it to stop, something like this. With the car, you said car is not moving by itself. It's moving by engine, right? Engine is applying force to the wheels.
But it's applied force when you put the force on it, but it's on the gas pedal.
You're not applying force to the car. You're applying your force to the gas pedal, but actually the gas pedal only regulates the engine. Engine is the main force. It's much stronger than you. You know how many horses powers is in your car? Well, Antosha should know. Your dad should know. How many?
300.
300 horses.
And how many little boys is one horse?
So this is in your car, right? So it's a big, and you should understand that a human is about usually the average power of human is about 1/10 of the horsepower. 1/10 fraction, small fraction.
Oh, wow.
So if you talk about humans, right? So your car is about 3,000 humans.
Or probably 6,000
That's-
little boys.
That's the problem. So that was for Aristotle. Aristotle was thinking about that the thing would not move if any force is applied. Actually, you should understand also that Aristotle lived in the so-called slave society, right? Slaves were the main force. Slaves and animals, right? And if you're not pushing not pushing the animal, they would never work. They would never move. You know? Or they move by themselves, but at their own thing. But if you're talking about, if you want them to move, they would not. You should force them. Some question you said? Oh,
Or like when you're typing, like it won't type unless you put pressure.
say it again.
Like a keyboard, it won't move. I mean, like the letters won't get on if you don't apply pressure.
I'm not sure what you mean on the keyboard. Keyboard what? You press the button. That's what you mean. You press the button and then what?
And then the key moves.
The key moves. Yes, the key moves because you press the button. Yeah, you applied force, right? Yeah.
But then it stops moving when you stop pressing.
Okay, yeah. Sometimes it makes to reverse, but that's another thing. Okay, Aristotle thought about many things, but not that many as the history shown after that, right? But he was the first. So anyway, he was the first. So later comes already in the 70s, 70th century, comes another big scientist in physics. His name is Galileo Galilei. So Aristotle first, then Galileo. Galilei. And he was Italian. He lived in between 16th and 17th century, and he came to a few main principles in physics. First principle is the principle of relativity. It's called Galileo principle of relativity.
Wait, that was Galileo? He did relativity?
Yes, it's not relativity of Einstein, it's relativity of Galileo Galilei. It was the first principle of relativity, and it stayed until Einstein came. So from 17th century, 17th, right? So up to 20th century. Einstein come in 20th century. So
Einstein from the 20th century?
so 3 centuries it was there. This principle of relativity of Galileo Galilei. And this principle of relativity, what it says that we talked about that actually. That if you move without changing your speed, right, like in straight line, and without changing, without acceleration, everything looks like it's the same. It's like you're standing, like there is no move, right? Like if you sit on the moving ship without waves, right, and ship is moving very slowly, you won't find anything strange around you. Everything will be okay. You can go, you can sit, nothing changed. Everything, like if you drop some weight, it will fall down like regular way, all normal, right? So the principle of relativity said that all is called inertial reference frames. So like a moving boat, right? Without on the ocean without waves, it is inertial frame. It is called inertial frame. Or a car which is moving around, which is moving on the very straight and very, very good road that you cannot feel anything, no vibration, no nothing. Again, it will be the same if you try to make some experiments here or some experiments here, everything will be okay. Whatever speed is going, speed may be anything, any speed, but it should be straight without changes. And that was this principle of relativity of Galileo Galilei. The other main thing for him, for Galileo, was his study on falling objects. He actually was born in a famous, pretty famous city in Italy, which is called Pisa. Maybe you remember why it is famous? Mostly. Yes, there's a so-called falling tower of Pisa, right?
Yeah.
And he actually, Galileo, he used this, exactly this, falling but not falling actually, tower, right? He was dropping different things from here. And
That's an urban myth.
huh?
That's an urban myth.
Say it again?
Nobody really knows if you drop stuff from up there.
Okay, but it doesn't matter.
So what he did, he put like metal balls, right? Metal balls. Then of the same size, but different weight, like wooden balls, right? So wooden balls, some other balls. He was dropping them from the top. Level, top floor, right, of this tower, and watching. There were two of them actually. He was measuring here when they dropped, and his like apprentice, he was dropping them at the same time, like few balls, right? One ball is like metal, very heavy. Another is like a wooden, partly heavy. Another like maybe empty inside, right? Some wooden, but the same size but empty inside. And he was measuring how they fall. And he found out that they actually fall almost at the same time. Whatever weight there.
So regardless of the
Regardless of weight. Regardless of weight. And-
That's for paper, but then paper could unfurl and then
Right, paper feather, right? You drop feather will fly, right? And very slow. But actually, okay, but he said he make a law out of this. I don't know the name of this law, but that all the fallen objects come. He postulated it. He said that in normal circumstances, he understood that there is air actually, which actually make things to fall differently. He understood that, but he think that if it would be no air, they will fall at the same time. They will fall at the same time.
But then that's space. But space, nothing moves unless you put force
Okay, I think in just a second. In what time? In 1971. Compare, right? This was about what time it was? It well, like 1632 or something, right? These experiments 1632, right? And 1971, it's already 20th century. So 340, almost 340 years later, right? The astronaut, American astronaut, David Scott, he tried this on the moon, on the surface of the moon. He dropped his hammer, metal thing, right? And the same, he dropped it, yes, and the feather. He dropped them simultaneously and watched that they fell down at the same time.
Because there's no air.
Because there's no air. Mm-hmm. So this clean experiment, was done 300 years after actually when the law is discovered actually. So he could not go to the moon, right? But he actually discovered this law 340 years before any real experiment can be done with this. So he's pretty smart, but it served a bad thing to him. In the next year, actually, he found it in 32. In 33, he was imprisoned by Inquisition, by the Roman Inquisition, imprisoned for life, actually. But he was already old. He was almost 70 years old to the moment. So they decided to change it to the house arrest, right? His home arrest, where he stayed until his life, like for almost 10 years later. He never left his home.
Oh God.
That was his, yeah. So that was Galileo Galilei, right? And now comes another guy, which is considered probably the greatest, not the greatest philosopher or scientist, but the greatest physicist, right? Because he made lots of discoveries, and his name was Isaac Newton. Isaac Newton, he's British scientist. He lived in 18th century, between 17th century and 18th century. And now we talk to him a little more because he discovered what is called laws of mechanics, laws of mechanical motion. And many other things also, mostly, by the way, interesting enough, he made a lot of things. He was not only, by the way, a physicist, he also a theologian.
A what?
Theologian is a, you may say, scientist who study the things about God. He was a big believer in God, and he. Yeah. Как там посвятить? Devote?
Devoted.
And he devoted his main work, principles of natural principle of physics. He devoted it to God. So he was studying on physics, on this, on that, and God. And also many of his discoveries he made by just 2 years of his life. It was the times of a so-called Great Plague.
Wait, the bubonic plague?
Yes, the Great Plague. So these times he had to go to the village and sit there for 2 years, and he discovered all of his laws, mechanical laws, law of gravity, and some optical things, very interesting things, like, for example, the spectrum, there's a prism, like when the light comes to prism, right? It is separated to different colors. He discovered this and many other things. He got a theory of colors, actually, on that. And that was done in the times of Great Plague. He also made many things in his life. Okay, but we will talk about mostly physics. If any questions, just say. Antosh, question?
No, Vijay has some question.
Okay, Vita, what's the question?
So you're saying that Newton once had
Yeah,
So he just did it just to impress the God he believes in?
yeah.
Oh.
Actually, most of those guys, most of them, they were believers. Like the scientists that are atheists, they appeared only at the end of 19th century, not that long ago. Even in the 20th century, many scientists believe in God. But Newton was like a big believer, right? So one of these things, he really thought about it. He tried to find some laws on this, and so it's different stuff.
So instead, he discovered the laws of mechanics instead of trying to prove. So he accidentally proved laws of mechanics instead of trying to prove God exists.
He believed that his work proved the existence of God.
Yes.
Actually.
Yes.
Really?
Yeah.
Exactly. Yes. They were thinking that such a beautiful world only can be created by God because it's so beautiful, so harmonical and everything. So it should be like there was one of the biggest thinkers, Roger Bacon. I think Bacon. I think if I'm not.
Roger Bacon, a philosopher.
Roger Bacon. He actually considered that the whole world is actually a writing.
What do you mean writing?
The laws of nature and everything. He considered the book, the sacred book of God.
Like Charles Darwin.
He said that this is the first. He called it natural. Natural testament or.
Natural selection.
No. Pizza, you can.
Как там будет Евангелие уже?
Roger Bacon, he said that the world around us is a book that we're reading.
Yeah, which is written in objective
And it
things.
was written by God.
Yeah.
Wasn't it called like Universalia or something like that?
It's just a small example. He was not a physicist, but anyway, Roger Bacon was a pretty smart guy who, by the way, he visualized like the cars. He lived, I think it's 17th century or something. He imagined that the world with the cars, flying planes and everything, like lots of things that we have now. He just thought about it. He wrote about it.
The Divinity or something like that with the
Yeah.
Okay, guys. So now let's return to Newton, right? So Newton. He was known mostly for his, but many things. But one of the three laws of motion, of physical motion. The first law says that if you not apply the force to something, like watch what Aristotle said and what Newton said. He said, if you do not apply any force to any object, right, it will stay on his place or move with some speed. Speed would not change indefinitely.
Did you hear that? This is very different from Aristotle.
Indefinitely. Remember, Aristotle says that if you leave alone object, it will stop, right? And Newton said, no, if you leave object without force, it will go indefinitely with no change in acceleration, no change of the speed, indefinitely.
But that's inertia in space.
And he called it inertia. Yes, this is the law of inertia. And that's why the reference frames which are moving without change on speed, right? They are called inertial frames.
Can I ask a question here?
Yes.
But then how the cars? Why do the cars stop even though you accelerate them? Then you stop accelerating them and they stop on their own. How come they don't go forever?
Okay, so taking into consideration this law, you should say that there is some force which is actually applied to your car. You just don't know what force is it. But he said that yes, objects are stopping by themselves, right? But it means that some other force is applied to stop it. That was Newton, understanding of the things.
And Aristotle, the air and the friction, and the Aristotle just assumed that there is always. Oh, okay, no, that makes sense, right, Vita? Okay.
Okay. Yes, actually, if you're talking about car, this is called the force of friction. Yes. So when something is moving on the surface, like a car or whatever, right? There's a friction which goes between a car and the surface. And this friction is a force which stops it eventually, sooner or later. Depends upon how good is the car and everything. So the second law is the law of, just it's called second law. It's the first law, it's called second law. This is the law of movement. So, and it says a very simple thing, that if you apply force, some force, which we'll talk a little later, what force is that? Any force, it will give the mass some mass. Remember mass, right?
Yeah.
Some acceleration, A. These things means that those things are vectors. We'll talk about vectors. Maybe you remember. We talked about vectors a little before.
Yeah, I remember.
Remember? Okay, good. So both force and acceleration and actually speed and many other things in physics are vectors, right? So this is so.
It is-
Actually, I was thinking of velocity, but I thought it had nothing to do with this factor.
And if you remember the previous, we'll talk about a little about vectors a little later, but we'll talk about them a lot actually. But anyway, from this you can find out in what units is measured the force. Okay, mass is measured in
A kilogram.
kilograms, and acceleration is measured in
Distance over time, which is meters over seconds.
acceleration.
Oh, acceleration meters over seconds squared.
Right. So this is the unit of the force. This is the unit of the force, and because of Newton, it is called Newton. It's called Newton.
Mass and acceleration.
Kilogram times mass.
Kilogram, meter
Times meter over second squared.
over second square. It is called Newton. This is the measure of the force in this C, in the system, in the C system. Remember C, System International, right? So, like for example, there is a force of gravity, right? There's some force of gravity. We know that, right? So force of gravity is that if it applied to the mass, like something that's dropped, right? Like your mass is, how much like Vitya? What is your mass?
Like 30 kilograms.
30, right? So 30 kilograms, right? And the force, which force is applied to you? We know one interesting thing that is measured, I believe, by Galileo, actually, that when you drop something, it will accelerate, and acceleration is 9.8 meters per second square. So each second, your speed will make more by 9.8, almost 10, right, meters per second. Each second it will be growing by this amount.
Yeah, it is square.
Yeah, but means acceleration means change in speed, right? Change in speed. So the first speed is 0, right?
Yeah.
After 1 second, it will be 9.8 meters per second. After 2 seconds, it will be, another 9.8. So it will be 19.6 meters per second. And that goes like this. This acceleration of the Earth, right? Earth gravity acceleration. It is called special name G. G is 9.8 meters per second square. It's acceleration in the force of gravity of Earth.
Something else.
Something else?
Acceleration of
On Earth.
Earth.
On Earth.
Free fall.
On Earth. If you are on the moon, will be different. Will be 6 times less than this. So it's about 6 times 1.1, something like this, meters per second square. And the Jupiter will be much more, or whatever, right? So you can find out. But for the Earth, it's called G. That's why maybe heard like we have acceleration like 9G or 2G, 3G. You probably heard it, or maybe from science fiction stories or whatever. Like the rocket gives you like 10G.
Oh yeah, like in
Overweight, or how they call it.
Exactly. Like in that world.
Yeah.
Got it.
So we have this law that the force is connected with the acceleration. So if something is moving like by itself with a certain speed, no force is needed, nothing is changed, it's going by the first law, going indefinitely. So but to change it, you need some acceleration, and you need some force to be applied. So if something is accelerated, it means that the force is applied. If you apply the force, you have certain acceleration. So they're interchangeable. Yes? Yes?
Is Aristotle and Newton both right, or is one of them wrong?
They were in a certain way. Aristotle lived in the times that lots of things were not known, right? Newton was already at the point where he was thinking about space things, right? He was thinking about astronomical movements. He thought about like planets and stars moving around, and he understood, not too many people understood, but he understood that in space there is no air, that everything is moving like indefinitely. Remember why he found this law, right? So he was thinking out of this Earth box already. That's why he was right? But Aristotle was right inside this box, because on Earth, right, there's nothing which moves indefinitely. Actually, we found out something in 20th century. We found out maybe you remember, some things that move indefinitely. Maybe you can remember that? Indefinitely, really.
Air.
No. Air stops. If you put air into this like
Then a
light, actually light stops too. So light it's not like stopping like per se, right? But it's stopping by disappearing. It dissipates. Huh?
What about light?
What about what?
What about light? Light stops too. You die. I meant like you die. For everybody. That doesn't stop. No, that's what I meant.
We're talking about motion. We're talking about physical motion, like mechanical. Not about other things. Mechanical things. Just the motion of objects, right? So there's no object on Earth. There are, but before the beginning of 20th century, nothing was found that moved indefinitely. I can remind you, there's in 1911, so just the beginning of 20th century, right? The Dutch guy from Netherlands, right? He was a scientist. He found out that with the low temperature in the circled wire, the electrical current may never stop.
Oh, wait a second.
This is called superconductivity. And a little later, I forgot who, found out that it's the even lower temperature for the liquid helium. Liquid helium. It will never stop in the tube. If it puts to motion in the closed tube, it will run there forever.
So liquid helium, if you put it in the tube, it never stops moving.
Oh yeah, now I remember.
Not the regular, but so-called superfluid. Should be very cold liquid helium.
I remember you told me that.
Yeah. I think I remember. Yes. Okay, so but this was found only 1911 and a little later, in 1920 or something, like for the liquid helium. So we will talk now about the third law of Newton, which is important. And what else? This a sec. What's the name for this? Yeah, action reaction. Sometimes they call action reaction, but usually they call it the third law. And the third law says that if you push something, if you apply force to something, like for example the wall, right? You have the wall. You are standing here, right? And you're pushing with your hand to this, with the force F, pushing the wall. Probably you can feel. If you try right now, you will feel that the wall is pushing you with some force too.
Exactly. Can I tell you why? I think I know why. Because atoms never touch. Because they always repel each other.
Yeah, so that just pushes you back.
Yeah. So when you fall, it's how hard the atoms push to not touch.
So you push the wall, right? And the wall pushes you. And Newton said that this force is exactly the same, but the opposite in direction. So this is action, this is reaction. And that's why the wall is not moving anywhere. If the wall is steady, right? You hear me, right? Guys?
Yeah.
Because okay, so you hear me. So I understand what I'm saying, right? So if you're pushing the wall with one force, the wall is pushing you back. And that's why the wall is not moving anywhere.
Wait.
The lights just went out.
Probably.
That's on.
The bedroom is open. I mean, the lights on in the bedroom is not just.
Mine's on.
Yeah, it's just that. This is off too. Yeah. I know that the bulb's just burnt out.
Yeah, but then all of a sudden the computer turned off too.
Guys, are you listening to what is going on there? I can understand.
No, I understand. You guys have the computer on?
I don't know.
Maybe that's what happened.
Hey, Papa!
Okay, it's back on.
Back on what?
Okay, you know what? Dim is on. Was it the heater?
The power went out.
Guys, what is going on there?
The power went out.
The power went out? I can hear you. Do you hear me?
Yeah.
Yeah, now it's all back on.
So now you will continue? May continue?
Yeah, VTAP. Okay, the power's back on. The second law is F equals ma.
Did it ask what happened?
Yeah, the power went out. Oh, I like the little guy. Look at that.
Oh, wait. Wait, did that?
It looks like Pinocchio.
Hey,
Okay.
did that?
Yes.
What's up gonna be?
Oh, well, wait, VTAP.
Oh, yeah.
Why are you jumping?
So the wall is not moving anywhere. Why? Because the force of reaction which walls pushes you is the same with you push the force, the wall. So you push the wall like this, right? And the wall pushes you and nobody moves. Another example of this action-reaction law is when the car, okay? Your car is moving along the road with the constant speed. So V is constant, not changeable, not changing. So you're moving, right? Your car is moving, right? With a certain speed. And you know that the engine, actually, the engine is moving your wheels, right? With a certain force. So it's applying force to the road this way. You can hear me?
Yeah.
Okay, but if the force is applied, right? How can it be that the V is not changing? V should be changing, right? According to the second law, you should have acceleration. The V should be changing.
Well, it does. So like.
How is that? No. You sit in the car, you run, you ride, right? Everything's okay. Your car is moving. You can maintain certain speed. V is constant, right? So you're moving. So you're applying certain force to the road. And why the speed is not changing?
Because you're at max speed.
Because what?
Because you're at the max speed.
What max? You put your gas pedal more to the metal, right? You can increase your speed. It's not max.
No, I meant like max amount.
What is limiting it?
No, what's limiting at the moment? Something definitely is limiting, right? Because it should be changing, but it's not. Friction, exactly, friction. And you know where friction goes? When the force you apply is moving here, where the friction goes?
In the wheels.
Yes, at the wheels, but at what direction? Backwards, exactly. So you apply the force to the road, right? And the road applies the force to your wheels. This with the same force, but opposite. And this friction force actually moves your car. This reaction moves your car.
Wait, so it's not the actual. Wait.
No, it is action. Yes, this action, it moves the road, but the road reaction moves you.
Wait, so you're saying without a road with high friction, a car wouldn't be able to go fast?
Just imagine low friction at first. That your car is standing on ice. What will happen?
Can go nice. Think about that.
Well, not very, because it's gonna go slip.
If it's a very good ice, your car is not going anywhere. Actually, it will be on one. It will be standing. Your wheels will be rotating, but you are not applying any force because there is no friction. You're not applying any force. There's no friction force, and you're not moving anywhere. You should have a good friction. That's why the wheels are made of rubber, and not anything else, right? Not ice. You don't using like slippery wheels, right? You have something really unslippery, not slippery. So we have these things, and also a little long about this, but we should talk about just a little about one more thing, which he found. First of all, there are two so-called conservation laws, or conservation of energy. Newton was thinking about conservation of so-called kinetic energy. Kinetic energy is written like this: mass to the v squared divided by 2. So the things which is moving, it has this energy. And in certain events, it's conserved. Not all the time. So this is one conservation. Another conservation is conservation of so-called momentum. Momentum is a vector too. And it is mass multiplied by speed. This is momentum.
It's velocity. Velocity.
Yeah, okay, velocity. We're talking about speed. Okay, velocity, whatever. Velocity, speed, whatever. It's just v, right? So they're both vectors. Just understand.
Yeah, that's why I said that, because
Yeah.
vector. And momentum is a vector.
And if you have like what it means, conservation of momentum. So you may have many objects which are moving, like this v1, this v2, this v3, right? And this is m1, m2, m3. Different masses, right? And different speeds or velocities, right? So the momentum of the whole system is the sum of all it. So this is the sign of sum, summarizing, right? So it is m1 v1 plus m2 v2 plus m3 v3, right? So you summarize all these things. I'm sorry, not here. It's here. If you remember the vectors, if you add the vectors, adding of the vectors have special rule of triangle. Maybe you remember. We will not talk it right now about it, but just you remember this, and your dad will remind you. So you can add all these things together, and it will be whole momentum of the whole system, the whole thing, momentum, right? And then whatever happens there, they may collide, they may hit each other, run in different direction, everything changes. You wait maybe for an hour or so, and then calculate momentum again. It will still be the same. So it is constant. If you do not apply anything from above to this system, if system is so-called closed, so it's all that we have. And whatever changes there, the momentum is still the same. So it's a very, very important law and very powerful. And this is for the momentum. And the energy, interesting enough that kinetic energy is not actually conserved. It's not constant. It may go to like other types of energies, like the friction. When you have the friction, it goes into what's the name of this? Thermal energy. Antosh, what's the term for this?
Yeah, thermal energy.
Thermal energy, thermal. So the road, when you're riding along the road, your wheels become hot. Your wheels and the road will become hot. So they take some energy from your car, and that's why kinetic energy is not conserved. And that's why if you don't have the engine running, right, your kinetic energy will go into the heat all around, to the heat of your to the
catch on fire then?
high in temperature. The temperature will be high on the wheels and on the road, and goes and dissipate around, and your kinetic energy will be spent. So the conservation of kinetic energy, it's not conserved. In many cases, it's not conserved. But if you add some other types of energies, so like thermal energy, sometimes electrical energy, lots of types of energies, right? There was a lady which lived a little later than Newton. Emile, she was Marquise du Châtelet. So Marquise Emile or Emily.
Who was a lady?
Du Châtelet. Marquise. She was Marquise. So she found out that if you add some other types of energy, so they are conserved. The energy is conserved. So that was her thing. It was actually written in addition to another edition of this Newton's book. Actually, it was the published later. It was about like 50 or 70 years later, after Newton's death or something like this. So the book was published again, and she introduced there this law, the full law. Newton has this only kinetic energy thing. So she added the whole thing to this. Okay, so any questions on this?
Yeah, I have a question about the laws of physics.
Sure.
They're more of a conjecture that is proved by experimentation rather than a theorem proved through a logical reasoning, right?
I'm not familiar with this term. What conjecture? What do you mean under conjecture?
Well, no. They're so the laws of physics. They're just a guess, a good guess at how things should work, and they're proved and supported by the experimentation later on, right? They're not proved or derived.
So your question. So you question how the discoveries were made actually. Yes, mostly they are guesses of some philosophical guesses. Some smart people usually need it to understand, to guess something and to come to some conclusion. And this conclusion usually is very abstract and not definitely if you try to test it, right? Usually it's not correct. It has usually some problems. Like for example, Galileo found out that the things going at the same time, right, falling from the tower, right, but not exactly the same. If you really measure, you have errors all the time. You have errors. You see that something is going on. But he considered in his mind that if there is no air, there's something this and this and this. Taking this into consideration, they will fall at the same time. The same thing like for Newton. Newton never sit in the rocket, right? Never been at the moon, right? He cannot see that something is moving indefinitely without changes. There's no way for him to see. Right now we saw something, right? Like for a current in closed circuit, electrical current, right? It was tested for 23 years. 23 years the current was moving, and there was no change in current. So we know that it's pretty low, but still, maybe in 1,000 years it will stop, right? We don't know. Any experiment has certain range of the testing and errors and everything. Yes, what's the question?
How can they measure the current without affecting it?
Oh, that's another story. How to detect? When you detect, actually, you have the influence on the current too.
I'm not even talking about the quantum effect, but literally, if you measure the current, what do? You put a resistor in there, or you measure the field. All of those things.
How they did it exactly? They measure the field, right? Because the current is running, there is a magnetic field around. Yeah. So they measure the field, and the field they measure, it's like they put some, like for example, like a needle, like a compass needle, right? Like very sensitive one. And they measure the angle. Like 23 years they were measuring the angle, because if the current is lower, if it decreased, right, the angle will be different, right? So they were looking at this. They put it into vacuum, everything for 23 years. They're watching these needle or something like this, some magnetometer, sensitive magnetometer, the measuring of the field, and the angle didn't change. So they found out that it was not changed. So, but he didn't have anything of this, Newton, right? But he discovered these laws which stand very good. They stand from the 17th century until Einstein, who came in the beginning of 20th century. So the laws were changed, but also they were changed very slightly. So mostly they were changed to the events coming with the speed of light or close to the speed of light. And we'll talk about this a little later. Okay, any other questions, guys?
Okay, guys, get ready for the questions.
Okay.
About an hour.
Okay, now you're ready to write? I'll give you my questions. Okay. The first simple, just calculate. What is the force of Earth gravitation for your own mass? So what force, with which force Earth push on you with the gravitation?
What is the gravitational force
For each of you.
for each one of you?
Okay.
Yeah. You wrote, right?
No, not yet.
So you have, now you calculated like,
The force of what?
What is the gravitational force on each one of us?
From Earth.
yeah, gravitational force. So you calculate each of one, calculate the force. You know the force for you, for yourself, right? Now, looking at the laws and everything, the second question is, apply the force to you, which is equal to this force that Earth is applying to you. Force going up, the same as this force that you calculated. You got it? Apply this force. Is this force enough to move you to space?
So if a force equal to your to the force of gravity applied to you,
Okay, the force equal to the what?
force of gravity applied to you directly, will you?
Would it be enough for you to go to space?
No.
What's happening? Wait, what's next, Papa?
10 to 11.
Did you get it?
If a force equals to the force of gravity applied to you, what means?
Will it move you into space? But in the opposite direction from gravity, will it move you into space?
No, but then wouldn't it be out?
Tell me that the lesson.
But then if the force of gravity is on the other direction, wouldn't it all be equaled out? Cancelled out?
Okay, you think about it. Okay, yes, it's the same to the opposite direction, right? Would it be enough for you to go to space or not? This is the question. Just think about it. Consider all the things around you and everything. Think, would you go to space or not? And also, in addition to that, just another question. Would you be, if you come to space, I don't know, would you not? If you go, would you be weightless? Would you be weightlessness in the state of weightlessness or not?
While the force is applied to you? So would you be, yes.
Is it the third question?
No, it's sort of part B.
As if, in case that you decide that it's enough to go to space, maybe not. But if enough, so would you be weightless or not at this state? Okay, you got it, right? Now the third one.
No, we didn't get it yet.
Hold on.
Okay.
If you're in space and this force is still applied to you, are you weightless? You're in space, right? We had a discussion on this topic because we were at Pushkin
Okay. So you just decide, okay, and answer my question, okay? Now the third. You ready? Almost?
Okay, ready?
Okay, ready.
Wait, how many questions are there? 3. Wait, what's your 3?
Yes.
I thought it was like 3 or 4.
And the third question is like this. So you have Earth, right? It's Earth. And that's you. That's you. And you have certain speed, horizontal speed, moving like this. Just estimate what speed do you need, like having all these laws, but not talking about anything else, just the laws. Antosha, you help. That's, of course, you help, right? So, which speed do you need not to fall on Earth? You understand that something is going down, that something like this is acceleration of gravity, right? G. It's pushing you down, right? This force, gravitational force. There is a speed, certain speed or velocity, right? That you pushed. And you will go like this if there's no Earth, right? But Earth is going to you like this. So you are falling, right? All the time, and you're moving. So which speed is needed not to fall to the Earth?
think about it this way. If you're not moving at all, you will fall on Earth.
That's like international space.
If you're moving a little bit, you will still fall down, but a little bit farther. It's like International Space Station.
I can tell you something. This is what it does. Wait, guys. Wait, can I say something? Can I tell you what it does?
You got the idea, right? You can discuss it later. You got the idea.
Hold on. You guys need to write down the question. At what speed should you be traveling in Earth orbit?
No, you're not orbit. You are right here.
At what speed you should be traveling above Earth in order to never fall? It's effectively the orbit.
We need to know what the speed of the International Space Station.
That's okay. It's station, not station. If there is no air, like for example, there's no air.
If speed makes it go like it's gonna fall down, but then the Earth dips it around to go back up, so it never touches the Earth technically.
Yeah. Okay. Okay, guys.
What's the speed?
Antosha, you got the idea, right?
I got it.
So you got it. So you have the question. That's it. Okay. Some other questions.
Oh,
Wait, we have 4 questions?
No, I asking you. Any questions?
Oh, that's what.
okay. No, that's it.
No. Okay, guys. Antosha, do you have a camera working or not?
A what?
Okay. So